Welcome back to part 2 of our Containment Architecture Explainer. Okay, let's just dive right into this. Have you ever wondered why some independent cargo tanks on those massive gas carriers need a literally massive backup structure wrapped around them, while other tanks carrying the exact same stuff need basically no backup at all? It's kind of a giant structural puzzle. Today, we're going to crack it by looking at the 3 very distinct flavors of independent cargo tanks: Type A, Type B, and Type C. Now, just to set the stage and quickly recap our last explainer, we established that membrane tanks are, well, they're practically paper thin and lean entirely on the ship's hull for support. But independent tanks, they are totally self-supported. They sit completely separate from the hull, they stand entirely on their own, but as we're about to see, not all independent tanks are created equal under the law. Before we break down the specific types, we absolutely have to talk about the secondary barrier. Think of this as your ultimate insurance policy, mandated by the IGC Code. It's a required backup containment structure sitting right outside the main tank, and its one and only job is to safely hold that liquefied cargo if the primary tank ever fails. And here's the real kicker for today's explainer. The strictness of this backup rule changes completely, depending on just how rigorous the engineering is on the primary tank itself.
Let's get into Category 1, Type A tanks, or the classical vault.
So, Type A is the first, kind of most fundamental, and definitely the most heavily regulated flavor of independent tanks out there. They're usually prismatic, meaning box-shaped, which is super efficient for using up space inside the hull. But here's the catch. They are designed using classical structural analysis. And because engineers are relying on this older classical math instead of, say, advanced fracture mechanics, they literally cannot rule out crack propagation. If a microscopic crack starts in the steel, the classical math just can't guarantee it won't spread. Even so, they're still the absolute standard for fully refrigerated LPG and ethylene carriers. The other big thing to know is the operating pressure. Type A tanks operate at very low design pressures, typically under 0.7 bar gauge, so they're running right near normal atmospheric pressure, relying on heavy refrigeration instead of pressure to keep that cargo liquefied. Because of that classical math where we can't perfectly predict crack behavior, and because of those low pressure limits, the IGC code lays down a really strict rule. A complete 100% secondary barrier is absolutely required, no exceptions. You essentially have to build a full backup containment vault around the primary tank that can hold the entire cargo volume if things go sideways. Moving right along to Category 2, Type B tanks, the calculated risk. When we step it up a notch in engineering complexity, we see a huge regulatory shift. Type B tanks represent a massive leap in mathematical certainty. They can be prismatic, sure, but you'll usually see them as those super recognizable spherical Moss tanks, the big balls sitting right on the deck of an LNG carrier. They use incredibly advanced finite element modeling, strict fatigue analysis, and fracture mechanics. This means engineers can pinpoint exactly where a stress crack would theoretically start and prove with absolute certainty that it won't propagate to a failure during the life of the ship. And all that crazy rigorous analysis really pays off. Because the math gives us such high certainty, the strict IGC code relaxes. You don't need a full backup vault anymore. Instead, Type B tanks only need a partial secondary barrier. This usually just looks like a specially designed drip tray right underneath the tank. It's just enough to catch and contain a minor localized leak, which is literally the only type of failure the advanced math says is even remotely possible. Finally, Category 3, Type C tanks, the pressure fortress. If Type A is classical and Type B is advanced, Type C takes structural self-reliance to the absolute extreme. These aren't just cargo containers. They are heavy-duty pressure vessels. We're talking thick-walled cylindrical or bilobe shapes built to extremely strict pressure vessel design codes. You'll see these mostly on fully or semi-pressurized LPG carriers and more on smaller LNG vessels. Their wall thickness is so massive that the structural safety margin is inherently built right into the metal itself. Just look at the pressure capability here and contrast it with Type A. Type C tanks are rated for design pressures of roughly 17 to 18 bar gauge. That is massive compared to the sub-0.7 bar rating of a Type A tank. They are total fortresses, designed to aggressively hold high pressure without breaking a sweat. So, what does that extreme pressure rating mean for our backup rules? It means 0 secondary barrier is required, nothing. Zip. The sheer thickness of the steel walls and that massive pressure rating essentially act as their own structural insurance. The pressure rating is the safety margin, completely wiping out the need for any physical backup structure or even a drip tray. All right, let's pause for a quick active recall check to lock this all in. Think about the progression we just talked through. Which independent tank type requires absolutely zero secondary barrier at all? It's Type C. Because of that heavy-duty pressure vessel construction and the high design pressure, the tank's own strength completely replaces the need for any physical backup. This really sums up the entire picture into one perfect mental snapshot. Notice the beautiful inverse relationship here. With Type A's classical analysis and low pressure, the code demands a full backup. With Type B's advanced math, the backup drops to a partial drip tray. And with Type C's hardcore pressure vessel standards, the need for a secondary barrier drops to absolute zero. As engineering rigor and pressure capacity go up, the physical backup drops away. It's just a brilliantly elegant system based entirely on math and physics. But understanding how these tanks are engineered is really only step one. You can't just drop a giant steel fortress into a ship's hull and call it a day. What actually happens when these massive structures shrink from the extreme cryogenic cold? Or what happens if the hold spaces around them flood, and these massive, lightly loaded tanks try to literally float upward and tear themselves out of the ship? Well, in our next explainer, we're diving into construction and support standards, cradles, anti-float brackets, and the very strict 15-day rule for emergencies. It's going to be a great one. So until then, keep learning, and thanks for joining me.